Okay, so thank you very much. So let me start. I just kind of noticed that you have that there's 3 boards rather than 2 here, so didn't notice that at first. Sorry about that. So let me start with, instead of starting with a slogan, let me start with just kind of a quick review. So what we've said is that one category is a category, kind of tautologically, a category enriched over sets. So A, X, Y, we have an A, and for X and Y objects is a set. And an infinity category is a category enriched over spaces. So AXY is a space. Now, we could kind of comment just on the side here, which is that this passage from sets, thinking of a set and taking sets and thinking of them as spaces, replacing sets in our philosophy by spaces, that's taken on a whole new life of its own with this notion of homotopy type theory. And so you might say, if you're into homotopy type theory, what we're doing here is kind of philosophically very closely related, although let's not get into any. There might be specific relations, but let's not talk about those. Okay, so now the question then becomes, how do we work with these things? So there's a very rich category theory. You can do tons of stuff with categories. And we would like to just say, okay, let's just do the same thing with infinity categories, just keeping in mind that whenever you see a set, in certain places, you're going to replace it by a space. Okay. Now, to kind of work efficiently and to be able to do that, what's really turns out to be a extremely useful tool is the notion of Quillen model category. So what's a Quillen model category? We have a category M. This is a 1 category. I emphasize 1 category because, as you may have noticed, there's sometimes people say, okay, we're just going to use the word category to mean infinity category. I'll try not to do that here, but to be precise. But anyway, this M is just a usual 1 category. Then we have a W, which is a set of what's called weak equivalences. So what we should think here, the main example here is where M is the category of simplicial sets, and W is the category of weak homotopy equivalences. Okay? Then we have a notion of cofibrations and fibrations. So let me not get into all the axioms and stuff like that. But so what's going on here? So the basic idea is that we would like to calculate the localization. So this is sort of a machine to calculate okay. So we'd like to calculate the localization, and you might say the modern way of thinking, we're really calculating this infinity category here. So the model category structure is a way of being able to calculate this infinity category. So this localization, as we've seen, this is the Dwyer-Kahn localization, which is really an infinity category. Or you might think in the more old-fashioned way that we're trying to calculate the Gabriel-Zisman localization. Okay. So in the case of spaces, this is going to be the infinity category of spaces, okay? So that's the infinity category where this mapping space is the mapping space between 2 spaces. Okay? And so let me just kind of quote Bertrand Tohen here, who says a model category is sort of coordinates. I think he's the person who invented this phrase. Model category is sort of a coordinate system for an infinity category. Okay, so that's one relationship between model categories and infinity categories. So one relationship is that certain types of infinity categories, the big ones that have lots of limits and co-limits and stuff like that, tends to come from this construction of taking the localization of a model category. Then in that case, you can pretty profitably forget about the infinity category and just work with the model category. That's one thing you can do. But what we want to do today is we really want to use this to get a hold of the homotopy theory of infinity categories, because the problem here is that since we're talking about categories enriched over spaces, there's a lot more homotopy theoretical aspect, which was already present in the theory of categories because you had this notion of equivalence of categories. But you could kind of deal with that, and sometimes you have to talk about a two-category natural transformations and stuff like that, but you can sort of do that by hand. In this setup, there's a more serious amount of homotopy theory going on, and so we would like to have a model category of infinity categories. So let me just kind of mention, but maybe I won't write down on the board. So I think one of the reasons, if you want to sort of historically analyze what was going on, so I was saying, why Siegel could perfectly well have defined Siegel categories in the 1960s. I mean, all the basic tools for infinity categories were there in the 1960s. But there's some stuff which happened since then in the theory of model categories. Namely, there were a number of contributions by people like Bausfield, Jardine, Voevodsky for his A1 homotopy theory, and Morel, and Dwyer-Kahn also, and I'm sure lots of other people. There were, in the 70s and 80s and early 90s, there were a lot of developments of the theory of model categories, which we can then use those kind of ideas to investigate the model category theory of infinity categories. So you might say that, I think that's what leads to us being able to develop a technical environment in which we can work with these things. So that's what I'd like to start off talking about today. So we can define some model categories. So eventually one might want to say we want to work in the infinity category of infinity categories. So if you define some category of infinity categories, one category, then you localize by the Dwyer-Kahn equivalences, you'll get an infinity category. But that's a little bit circular, so we're going to have a hard time getting off the ground trying to use infinity categories to talk about infinity categories if we don't have somewhere to start. So that's why it's important that this notion of model category that already existed is really a good replacement for infinity categories in the sense it's an infinity category with a coordinate system in some way. Okay. So to work with infinity categories, we'd like to construct some model categories of infinity categories. Okay. So number one is going to be simplicial categories. So one is M is the category of simplicial categories. W is the Dwyer-Kahn equivalences. I think I defined those last time. So remember, that's morphisms which, on the morphism spaces, induce homotopy equivalences. That's fully faithful. And if you truncate down to, say, the set of equivalence classes, it should be surjective. So fully faithful and essentially surjective. Right. So that's a good remark. So what do I mean by when I make this statement? So there's lots of different objects there's lots of different sort of theories of infinity categories. So there's lots of different types of objects which we would like to say are infinity categories. And that's going to be the subject of in just a little bit. So for each kind of different type of object, we're going to try to construct a model category, or maybe several model categories, which allow you to work with that type of object. Okay. And then that's gonna provide a framework in which we can make comparisons between the different theories. So the first, our first version was simplicial categories. W's Weierkran equivalences. And so what are the cofibrations? These are what you might call free cell additions. Okay. So what do I mean by free cell additions? So think of having a category enriched over spaces. If you want to increase a little bit the size of one of those spaces, you might add a cell onto that space. And then that's going to generate a bunch of other cells where you compose that cell with all the different other maps. So if we add a cell to AXY, we sort of add a cell. We have this composition AXY and AYZ. So if we add a cell here, then we're going to have to add that cell across this entire space over here. And just keep doing that in all possible ways. That's what you might call a free cell addition. Okay. Yeah.
Simplicial categories are more familiar with the algebraic world for me, right? As chain complexes. And I guess in characteristic 0 it's the same. So one of these things that's chain
No.
Instead, what would free cell addition mean?
No. A simplicial category is not the same thing as a chain complex.
No, but a simplicial set. So
Well, that's kind of true.
I should be able to think of A of X, Y as a chain.
We can do that. So that was going to be my chapter a little bit later. If you have a DG category, so if you have a differential graded category, then A of XY is a chain complex. But the maps are not really from product. You wouldn't put a product here. You would put a tensor product here. So there's a construction which takes a chain complex and gives you out a simplicial set. It's called Dold-Puppe. You first have to truncate the chain complex into a negative strictly to less than or equal to 0 degrees. So if you take a DG category, truncate the morphism complex to degrees less than or equal to 0, and apply Dold-Puppe construction, you get a collection of simplicial sets, and that is indeed a simplicial category. So, and that's the relationship between DG categories and simplicial categories.
That was not my question.
Sorry, but anyway, that sort of set things.
But was allowing us to replace this product with a tensor product, which I agree is necessary. What does free cell addition correspond to in chain?
Okay, in that setting, if you want to freely add a cell here to say a chain complex, it basically means you're going to just add a generator to the chain complex, and you're going to say, you're going to say what D of that generator is. But that's a good point, which is that if it's chain complexes over a certain ring, then you'd like your modules to be projective, basically. So the notion of like a cofibrant object in modules over a ring or chain complex over a ring, basically, roughly speaking, means that the elements of the complex should be projective modules. So a cofibration, I should probably have said that here. A cofibration is something which it's good to map out of, and a fibration is something that's good to map into. So a fiber object is something where the objects are going to hopefully be injective complexes. So, and here you might so you want to add a free module.
But adding a free generator to the differential grade algebra is more than just adding free modules.
Yeah, then you have to add it as a generator to the differential graded algebra, as you say. What he's pointing out is that if you have a DG category with only one object, that's the same thing as a differential graded algebra. And there's a model category structure on DG categories, which is kind of similar. Does that kind of answer the question? Thank you. I think that was probably a useful discussion. So, without getting to all the details here, basically cofibrations are free cell additions in this world. Fibrations are things which are basically fibrations of the simplicial sets, I think, and if I remember correctly, we should ask Julie here. Fibrations of simplicial sets and satisfy a certain lifting property for equivalences. So anyway, so we have a model category which works that way. And this is, in fact, due to Julie. The next one, so the next version, let's let M equal Siegel categories. So in fact, but not Siegel pre-categories. So what's a Siegel precategory? So remember we had what was a Siegel category? A Siegel category was a bisimplicial set which had the property that the A0 piece was discrete and satisfied some homotopy condition about direct products, that the Siegel maps should be weak equivalences. That homotopy theory condition is not going to be preserved under any kind of categorical operations, right? Because if you start doing push-outs of things that satisfy some sort of up to homotopy condition, there's no reason why the push-out thing or the pullback thing would satisfy the up to homotopy condition. And one of the key points of the model category theory is that M is supposed to be closed under limits and colimits. So to get something which closed under limits and colimits for Siegel categories, you have to relax your condition and look only at bisimplicial sets that satisfy, you can require the first condition. So these are bisimplicial sets such that A0 dot is discrete. In other words, it's constant. The zeroth term is constant in the second variable. Okay. But now we don't know how to define equivalences. So now the point is that there's this operation called Siegelification. Now our objects of our category are no longer Siegel categories, so they no longer have any kind of composition rule. They have the simplicial structure, which if the Siegel maps were equivalences, then it would lead to composition like I wrote down last time. But these objects don't have any sort of composition rule a priori. So what do? You say, okay, let's do a Siegelification operation. So we're basically forcing the Siegel condition. So let's recall the Siegel conditions were the A(n) mapping into A1 cross over A0. That this is a weak equivalence. Remember, these are all simplicial sets because this is a bisimplicial set. So here we're taking the first simplicial variable. These things are all simplicial sets in the second variable, except the A0 is just a discrete set, so this product here works out nicely. And then you can just try to force the Siegel condition. So that means every time you have, if this is not a weak equivalence, then for any cell here, you sort of add that cell over here. And then you add all the stuff that it has to map to. Okay? So it's kind of similar to that. Now, this is kind of in my mind, somewhat new operation. So what it really means, so the meaning of this is that a precategory, is viewed as a system of generators and relations. So a precategory A is viewed as a system of generators and relations that can then be used to define an infinity category Siegelification of A. Okay. So Now we use this operation to define what it means to be a weak equivalent. So then we say we apply the Siegel-ification operation. Now we have a morphism of Siegel categories. I mean, of course, the main point is that when you do the Siegel-ification operation, that's supposed to satisfy the Siegel condition, so it is a Siegel category. So that's a morphism of Siegel categories, and what we said yesterday, we have this notion of Dwyer-Kahn equivalence. The same as there. All the stuff you need to define the notion of essentially surjective and fully faithful is already contained in the Siegel category.
So just to be clear, if you take your M and localize all of your weak equivalences, this is the category, the infinity category of infinity categories?
Yeah, yeah.
Okay, thank you.
That's I mean, what you usually do is you usually would really take the subcategory of fibrant and cofibrant objects and then localize. That's tends to have better properties, but I mean, I think modulo possibly some technical assumptions which I wouldn't be able to reproduce here. That thing where you take the fibrant, cofibrant objects and take the localization, that's equivalent to just taking the full category and taking the localization.
So the fibrant objects are the Siegel categories?
That's not quite true. So the cofibrant objects the cofibrations are injections. Fibrant implies being a Siegel category. But if it is a Siegel category, being a Siegel category is just a homotopy condition, whereas being fibrant is a more sort of has lots more lifting properties inside it. And I think this is also I'd like to thank the organizers, right? It's my standard joke. I think this is also a theorem of Joule, which is that you can't actually characterize the fibrant objects here. They're objects which are reedy fibrant and satisfy the Siegel condition. Okay. So because you start doing a few calculations, I mean, if you take something that satisfies the Siegel conditions and replace it by a different equivalent, a different bisimplicial set, which is level-wise equivalent, but just any old other thing, that's also going to be a Siegel category. But it might not necessarily have good properties. But what is true is that if A is a Siegel category, and if A into A prime is a fibrant replacement, then this map is a decay equivalence. Okay. So up to decay equivalence, then I think it's even a level-wise equivalent. It means a trivial cofibration to a fibrant object. It means the injective. So this category is the category of pre-sheaves. I mean, it's a subcategory of the category pre-sheaves over delta squared. Actually, you can make a quotient of delta squared by contracting the zero across delta. So you can make a category. So that's just pre-sheaves over that category. So here M is a pre-sheaf category. So injections just means injections of pre-sheaves. In other words, injections of bisimplicial sets. Okay. Let's see how we're doing here. I think a little behind. So that gives us a model category. Now let me go over here, and I wanted to talk about some other models. Maybe I'll do this a little quickly. Sorry for you guys out there. So there's other categories. So we could take M is the category of simplicial sets. But inside here, the quasi-categories inside here, those are the simplicial sets that satisfy what's called the restricted Kahn condition. This was introduced in the 1960s by Boardman and Vogt, but it was kind of, as far as I know, it was kind of sat there in their book for decades. So this is Joyal Lurie. So this is another model for infinity categories. And this is the one which everybody actually uses because it's the one where the technical benefits of this version are so high. You might say that's the one which actually works the best. It's a little bit less obvious why, at least to me, why these things really correspond to spatially enriched categories. So let me just make a word about that. So we can think of so if A is a simplicial set, or let's call it X maybe. If X is a simplicial set, then we can think of it as a bisimplicial then. And then we can apply the Siegelification operation.
In what way do you think it is bisimplicial?
By just making everything constant in the second coordinate. So the simplicial variable here is supposed to be the same as the simplicial variable up here that I'm writing down on the board. So in other words, think of it as we should really think of those things as simplicial spaces rather than bisimplicial sets. And here it's just a simplicial set, so it's a simplicial discrete space. Okay, so if you take a simplicial set and think of it as a bisimplicial set, then you apply the Siegelification operation over there, then you get a Siegel category. And technically speaking, what people actually do is you can actually even do better. You can actually go directly to a simplicial category. I mean, I guess I think this was made in comments. There's an operation which goes from Siegel categories back to simplicial categories, or even Siegel pre-categories back to simplicial categories. It's kind of like a bar construction. So you can just apply that directly here. That's what people actually do. But in terms of our intuition, what we're trying to develop here, I think it's useful to think of the Siegelification operation. So what we're really doing is we're taking a simplicial set and viewing it as a system of generators and relations to define an infinity category. Okay? So what it means is that in the simplicial set, if you have an edge, that's going to define a morphism. If we have a triangle inside the simplicial category, inside the simplicial set, that's going to define a homotopy between this composition and this morphism. So kind of in a geometrically pretty clear way, simplices in this simplicial set give you relations among the arrows. The generators are just the one simplices. Okay? And the higher simplices give you sort of relations between those arrows. If you have like a tetrahedron, if you have a tetrahedron, there's two ways that say that these three compositions are homotopic to the third one. And if you didn't have a simplex that was filling those in, then you would actually get probably a circle inside the mapping space from here to here, kind of as we saw in the example at the start. But if you fill it in, then you're saying that circle is actually homotopically trivial. Okay? So this is really pretty geometric, and if you start thinking about it, the process of going from a simplicial set, thinking of that as generators and relations, and getting out a simplically enriched category. And so you say that A, like X into Y, is a weak equivalence if, again, Siegel of X into Siegel of Y is a decay equivalence. And again, you have a model category. Again, the cofibrations are injections. Should maybe write that here. We'll see in a minute that this business of saying cofibrations are injections has a good property. Let me just finish this kind of quick whirlwind tour of the different versions of infinity categories by talking about complete Siegel spaces. This is due to RESC. So this is, you might say, a sort of more advanced version because we need a definition before we can even get to the statement. So the definition is, suppose A is an infinity category. And by that I really mean an object, maybe a fiber object in any one of these model categories. So suppose A is an infinity category. Then we define iota A. We saw this yesterday already, at least, if not before. Iota of A, or the interior of A. It's the sub, so it's the subcategory where we only use invertible morphisms, so morphisms that are invertible up to homotopy. So you might say it's really, you take A mapped to tau less than or equal to 1 of A. Then it's just the pullback square of this inclusion of sets. So this is a one category where we truncate. So we just take pi 0 of all these spaces, of all these mapping spaces. And then in this category, we take the subgroupoid. So we take the biggest subgroupoid of this category. In other words, we only look at invertible maps in this category. So that's a groupoid. Then we let iota A be the set of all things here that go to invertible maps here. Okay. This is a infinity 1 groupoid. And that's what we were discussing yesterday. So what we were discussing yesterday is that, so in other words, it satisfies the condition C of Siegel. I don't think Siegel was calling that condition C, but that was condition C on the blackboard from yesterday. In the condition that the maps be invertible up to homotopy, this iota thing, just because we defined it that way. And so it realizes to a space. Let's call it realization of iota of A. And that's it. Remember, that was an equivalent. That operation was an equivalent. So iota of A is equivalent to the Poincare 0 infinity groupoid of this realization, which is not going to be true for A. I mean, you could try to realize A, and you could take a bisimplicial set and take the diagonal simplicial set. That's going to be some space. That's going to be sort of the hull, you might say, the spatial hull of the infinity category. In terms of localization, it's what you get when you invert all the maps, when you localize the infinity category and invert all the maps. That's going to be that space. That's kind of like the smallest space containing your infinity category. Whereas this iota thing is like the biggest space inside your infinity category. So this is like the interior part of it, and that other thing is the hull. Okay, but if you take the realization of, if you first take the invertible maps and then take the realization, then what we were saying yesterday is that the pi infinity of that space is going to be equivalent to this iota A. Okay, so that just corresponds to a space. Okay, so kind of the slogan, the mini slogan here is that infinity 0 categories are the same as spaces. Okay. And let me go over here. So then RESC's condition so RESC says, okay, this business of having a set of objects in our infinity category is can be kind of artificial because that set of objects is not an invariant up to equivalence. If we have an equivalence, here, if we have an equivalence of infinity categories, that doesn't mean that there's an isomorphism of the set of objects, as we know for categories. I mean, different equivalent categories can have different sets of objects. So Rezk's definition kind of repairs that problem. So he says, let's look at a complete Siegel space. So a Siegel space, this is just like what we've been doing, but this is already technically more complicated because it's a bisimplicial set such that you have a weak equivalence from AN into A1 cross over A0 and so on, the same writing of the condition, but A0 is no longer a discrete set. So A0 is it spells for space. And so we probably want this to be like a homotopy fiber product or something like that. So that's why it's technically a little bit more complicated. So even writing down the Siegel conditions in a good way is a little bit delicate. But so one thing to do is to assume right off the bat that your bisimplicial set is a reedy object, is a reedy fibrant object so it's a reedy fibrant simplicial space. That's going to take care of this. Yeah, that's something which is going to basically make these maps into fibrations, so that the fiber product equals the homotopy fiber product. Now, so that's a Siegel space. Now, what's a complete Siegel space? It's that the natural map from there's going to be a natural map from A0 into this realization of the iota of A. Whatever that, I mean, the part of the difficulty, you have to make sense of what that means kind of along the way as you're going. But there's going to be a map from A0 into the realization of this internal infinity groupoid. So if you did this for one categories, you would already be doing something different. So if you did this for one categories, this is the subgroupoid of the category. And this is the space, which is this set of isomorphism classes, but with a k pi 1 structure. So it's a space. It's the classifying space for the set of isomorphism classes. So you see, even if you do this for one category, you're still going to get a non-trivial simplicial space out of the deal. And the complete Siegel space is that this is required to be an equivalence. Okay. And again, there's a model category structure. So let me just kind of mention, without going into the details here, let me just kind of mention what's the advantage of this situation. The advantage here is that a map from A into B of complete Siegel spaces is an equivalence if and only if it's a level-wise equivalence. Because by this condition fixes the A0 thing to be something which is kind of a homotopy invariant of the category. Okay. So it's sort of fixing what you're talking about. You would like to talk about the set of isomorphism classes. So it's a little bit like in category theory. If you said, okay, I wanted to have a category where the set of objects equals the set of isomorphism classes, that just doesn't work too well because some objects have endomorphisms, have automorphisms. But if you say, okay, if you go to spaces, this might actually be a good motivation for why you want to go to spaces. I mean, if you go to spaces, then you can put the space of isomorphism classes, which is to say the k pi 1 space whose connected components are the isomorphism classes, but the pi 1 of each connected component is the automorphism group of that connected component. Now you get something which has this nice property that you can measure equivalence exactly by measuring equivalence of each of the levels. Anyway, so that's kind of finishing the review of all that stuff. Then, how are we doing? Not so well. I think Janusz's question may not get answered, possibly here. Well, so I'd like to, let me just, so the first comment here is that comparison. So Bergner shows gives equivalent equivalences between all these different model categories. Sorry? Oh, well, in your paper there's all of them, isn't it, right?
No, I didn't do any of the comparisons.
Oh, really?
That was, I think, quasi categories, the seagull ones are
So, who?
Joy Allen
Oh, okay, so I should put Joy All Tierney here.
and then Larry
Whatever. Okay. Yeah? She said that she didn't do it. I thought that all those were in her paper. There's a whole big diagram of equivalences in Berdner's paper, but she says not all of the ones between all the ones I've written down on the board here are not all necessarily in her paper, but I mean lots of them are. Anyway, so what I'd like to say is also Bertrand Tohen gave an axiomatization for the, of course, this is, as I said, a little circular in terms of introduction of stuff, but post facto for the infinity category. I think even for the model category, maybe. Was that for the model category? Maybe that was for the model category. Oh. Maybe I'm going too fast. And showed that any solution of that axiomatization is unique. Without writing this on the board, let me just mention that this uniqueness is kind of a fun little strong form of the uniqueness, which says that not only are any two things equivalent, but the space of automorphisms of those functors is just what you think it would be, which is to say that the space of automorphisms of a theory of infinity categories there has just one element, which is taking the opposite category. So the space of in fact, not only just the group, the one group, but the infinity group of automorphisms of the theory is equal to Z mod 2Z, and that Z mod 2Z is just the operation of taking the opposite category. So that says that this is really unique in a strong sense, and I think that, for me, that kind of partly explains why, if you want, you can sort of surgically extract this theory from anything you do, because, given that it's unique, it means that specifying such a theory just doesn't provide any new cosmic information in the cosmic axiomatization. Sorry, I'm writing smaller. For the model category of infinity categories. Of infinity categories. All these different model categories, they have, although I'm not sure anybody really checked that all the different model categories satisfy those axioms. But yeah. And then maybe I should just mention Barwick and Chommer-Pries. Gave an axiomatization for infinity n categories. We're sort of seeing infinity, well, we'll be seeing that a little bit here, but not going fast enough. Okay, so that was my first page. Oh, sorry, that was page one. No, that was page one, pages 1 and 2, okay, good. So now, what kind of techniques can you use? So the short story here is just that pretty much any kind of technique you can think of in category theory, you can translate into infinity categories. So but let me just mention the first of those, which is kind of important, which explains why we need these kind of other types of objects, and maybe why people at the start didn't see exactly what to do with simplicial categories. So the first one is functor categories. So we'd like to say, so if M has an internal Hom, and if it's Cartesian, and if the model structure is Cartesian, so what does Cartesian mean? It basically means sort of a compatibility between the direct product and colimits, and cofibrant pushouts. So you might say the first main question is, if we take two different cofibrant objects and take their product, is that still a cofibrant object? That's the thing which is not true for simplicial categories. Because remember, that for simplicial categories, cofibrations were free cell additions. So if you take a simplicial category and if you start with like the empty category and start making a simplicial category by making free cell additions, then you'd make another simplicial category by free cell additions. If you take the product, the product of those is not obtained by free cell additions. And so that means that the model category of simplicial categories does not satisfy this property, but the other ones basically do. So Siegel categories, quasi-categories, complete Siegel spaces, they satisfy this property. That's kind of that's why we were interested in having this property that cofibrations are injections, because injections kind of are more or less automatically compatible here. I mean, in particular, all objects are cofibrant because the map from the empty set into your object is an injection. So in these categories, all objects are cofibrant. Okay. Now what are we going to do with our Cartesian model category? So now we have an internal Hom operation. So Hom of A, B is sort of adjoint to the product. So it's defined by saying that a map from E into, if we have a third object E, a map from E into the internal Hom is the same thing as a map from A cross E into B. That's what I mean by internal Hom. But if you have a presheaf category, then it has an internal Hom. Okay? Now, if you have this Cartesian condition, maybe you can just write here because we're getting kind of done here. If we have this Cartesian condition, then if A is cofibrant, but all the objects are cofibrant, so if A is automatically cofibrant, and if B is fibrant, then Hom of AB is the correct homotopy type, has the correct homotopy type for being a mapping object from A to B. And this is again an element of M. Okay. So now we're sort of defining a category enriched over itself, basically. So, and that's what we would like, right? The category of categories is enriched over itself. If you have two different categories, the category of functors from one to the other is a category. So the category of categories, that's why it's a two category. It's a category enriched over category. Okay. So now we can define infinity cat. This is going to be what's called an infinity 2 category. That means it's enriched over infinity 1 categories. By infinity 1 categories, that's the stuff we're talking about. Let me not write this down on the board, but you can now imagine what an infinity 3 category is. It's enriched over infinity 2 categories and so on. That kind of goes all the way up. What is it? It's the objects are just fibrant objects, fibrant A's inside N in M. And if given A and B, then we get an infinity category. Ha maybe. Okay. So let me I just don't have time, I'm sorry, to go through all the different stuff you can do with that, but let me just sort of list that quickly. I didn't want to try to get to formulating some kind of something to say about Janusz's question. Let me just list these, but okay, you guys can go and look this up on the web. You can do pretty much, so this just allows you to do pretty much everything. So you can do, limits, co-limits. So something needs to be said here. You can do limits in an infinity category, or you can do limits of infinity categories. When that's going to be limits in the infinity 2 category, infinity cat. Okay. Limits, co-limits. Adjoint functors. Con extensions. You can define stacks. You have a descent property. The descent property is just something about a limit, okay? When you say given a covering, you have the nerve of the covering. If you have a functor from that covering to infinity 2 cat, to infinity 1 cat, then you can ask it to be an infinity 1 stack. It just means that the value on the big open set is equal to the limit of the value on this covering diagram, and so on.
When you say adjoints, does that include like the existence theorem for adjoints based on exactness of functors and stuff?
I guess I'm not a big expert on that, I have to say, but I think pretty much. I mean, let's put it this way. If it's not there, then I'm sure you can write a paper and prove it. Okay. It just completely works. And so on. And then there's also this notion of stable infinity categories. These are basically corresponds to spectrum enriched categories. So that's a big problem. I kind of wrote a preprint called Limits in N categories, where as you go on, it's more and more discussion of how to solve that type of problem. That you have to take cofibrant replacements all the time. Right here we said that the objects of here are fibrant objects. So, sorry, not cofibrant, but fibrant replacements. Here the objects are fibrant objects. So when you do this theory, you have to sort of make fibrant replacements all the time. I think that's why, like the fundamental reason why quasi-categories have such a great success, which is that since the notion, in quasi-categories, maybe I didn't say that, the fibrant objects are exactly the restricted con conditions. So in fact, here it's true that the fibrant objects are the same as quasi-categories. That was the question before. So some rather just taking the fibrant replacement functor here is just much cleaner, basically. So yeah. So quasi-categories is the theory which allows you to really do what I said here, which is you can do everything. Let's see. So I should maybe go over here. So I should just say that complexes. So DG categories are kind of contained in here, at least in characteristic 0. So and DG categories are related to an infinity category. A few caveats are needed. So, a DG to be a stable infinity category, you really need to have the shift operation. So, like DG categories that have a shift operation are going to be viewable as stable infinity categories. So there's some little details, some slight differences between all these different things. But then if you're interested in stuff in characters, in homotopy theory in characteristic P, then spectrum enriched is different from complex enriched. So these are categories enriched over complexes, thanks to the question before. We discussed that a little bit. So now I'd just like to finish by trying to reply a little bit to Janusz's question, which is what kind of thing can you do in algebraic geometry? So I'd like to propose the following thing. If we want to talk about moduli of algebraic varieties, what's going to come up if we want to do moduli of algebraic varieties? So suppose we have a map of algebraic varieties. Okay? So think of Y as being sort of related to the moduli space of varieties, and X is the universal family, then we would like to maybe look at the rational homotopy type of the fibers, X, Y, for Y and Y. And we would like to say that those form some kind of local system over Y. Let's say in characteristic 0, but you could also be in characteristic P and look at the sort of étale homotopy type. I mean, this is just sort of a little glimpse, you might say. So as you say, in characteristic 0, there's going to be some kind of Hodge theory. But what is this notion of local system? This is really going to be an infinity categorical notion. Which is not necessarily to say that you couldn't, talk about this without using infinity categories. I'm sure that will be seen to be possible. But it's still, nonetheless, this is really an infinity categorical type of thing. So this is the type of thing you would start thinking of if you start wondering about how can I use my theory of infinity stacks, basically. So in other words, this is going to be like an infinity stack over Y. And so this is kind of the reason why I was personally interested in this. We also need to have it be over Y, but it's an infinity stack over the site AF K. So if you want to fix rational homotopy type with coefficients in some field K, then you're really going to get an infinity stack over AF K. And I suppose we should really put D, although I don't personally know how to do that, but I think you should put a DF over here. So we should really have like a derived stack. But let me just say that you can do things like have a non-abelian Gauss-Manin connection. So Navarro Aznar wrote a paper where he sort of calculated the non-abelian Gauss-Manin connection exactly on this thing, on the rational homotopy types of the fibers. By sort of just calculating, you could get up to like the third order infinitesimal neighborhood of the diagonal in what you're defining the connection. But you can just sort of define, you can just kind of define the problem in a way you might say, this sort of just works automatically once you start talking about infinity categories. So let me just finish by saying that this non-abelian Gauss-Manin connection is going to fit into a theory of variation of non-abelian mixed Hodge structures. But so we wrote a few little preprints about that. One with Tony and Ludmil, and I also wrote a preprint about secondary Katayara-Spencer classes. This theory is not really, I don't think, fully developed at all. But you can kind of see here that we're at some point in life, we're going to be interested in trying to understand the Hodge theory on the rational homotopy type of the fibers as some kind of local system over Y. But that local system is not just a local system in the usual sense, it's a local system in the infinity categorical sense. And so we're going to have a sort of an infinity categorical notion of variation of non-abelian mixed Hodge structure over Y, of which, if you take, suppose the fibers are simply connected, if you take the family of rational homotopy types of the fibers, that is going to be a variation of non-abelian mixed Hodge structure. And in this setup, let me just finish by the comment, so I guess I'll have to refer to my preprint for that. But let me just say what happens. So that you have a secondary Katayara-Spencer class. So the Katayara-Spencer so the example, and again, as usual, you can sort of see this happening in the non-infinity categorical world. So the example is, let's take Z, a surface, with H0 of KZ different from 0. Let's take X as Z cross Z, where we blow up the diagonal, and then Y is just Z. Okay. So we take Z cross Z and blow up the diagonal. That just means that X is a family of varieties which are obtained by blowing up a moving point inside of Z. Okay? Now, in terms of variation of any quantity which you can think of, nothing is varying here, because any kind of topological quantity, if you move the point around inside X, that doesn't change any kind of topology in an infinitesimal way. And also, there's no varying Hodge theory. The mixed Hodge structures on the rational homotopy groups are not varying in that case. However, you can calculate that you do have a secondary Kadaira-Spencer class, which is to say that basically the tangent bundle, the tangent bundle of Y at a point Y acts, but this is C2, right, over the complex numbers, acts on the fiber. Okay. So it's going to act on this Hodge theory. The usual Kadaira-Spencer map in any direction is trivial. Okay. So any one-dimensional subspace here gives you a trivial thing, but an abelian group can act on a homotopy type in such a way that all of the actual endomorphisms are homotopically trivial, but the action of the abelian group of rank 2 has a non-trivial class, sort of in cohomology. And that class is actually, so Janusz will say, oh, but that's easy to see. That class in cohomology can just be seen by the fact that if you try to calculate, these are all smooth varieties in characteristic 0, so the rational homotopy type of the total space is just determined by the cohomology algebra. So what's really going on here is that in the cohomology algebra of X, there's a cut product, but that cut product, if you project it into the array, into the pieces of the Leray filtration, it's kind of trivial. But there's a piece of the cut product which sort of descends in the Leray filtration, and that piece of the cut product which kind of descends in the Leray filtration, if you write down what it really is, you're going to get something which is exactly this secondary Kadaira-Spencer class. So you might say that what this theory will sort of contain is that there's that thing that you see globally from the cut product is actually a local phenomenon on the infinitesimal neighborhood of the fiber. Okay. So maybe I'll stop there. Oh, yeah.
What was the question?
Write down the restricted Kahn condition. So the restricted Kahn condition says that you have inner horn fillers. So let's kind of recall. So we have X as a simplicial set. So we're going to have a map from Xn into sort of you might say there's like the boundary map. So I guess the easy way is, so if we think of this as the simplex, which is, in this case, it's the simplex considered as a simplicial set. Okay, so it's the simplex represented by the element n of the simplicial thing. We can take the boundary of that, and so a map from the boundary of that into X, that's going to be a diagram which is definable in terms of just the less than or equal to n minus 1 part of the simplicial set X, okay? So this is kind of, I didn't write, this is like the co-skeleton of X or something like that. But just in geometric terms. So now a filler condition. So if X was homotopically trivial, that would say that any map like this gets filled in, okay? That's only going to be true if it's contractible. The Kahn condition says if we take this guy and we remove, so we'll call this a horn. If we remove one of the simplices from the boundary, then that's called a horn. So for a 3 simplex, it looks kind of like a horn, right? If we remove this piece, then you have a sort of a horn, right? The Kahn condition for a simplicial set says that the map from here to here is surjective. So any map from a horn into X has a filler. And the restricted Kahn condition says that's true, but only for certain values of k. So you're not allowed to fill the first and the last. So you're not allowed to fill the horns where you throw out, the face, which is the complement of the 0 or the complement of the n. So just an example is the easiest example is the case n equals 2. The Kahn condition tells us that we can fill this horn, and this horn. But you can see that these two are not really sort of categorical looking. They're involving kind of inverting something. But this is the inner horn. So the restricted Condon filler just tells us, Condon condition tells us that if we have these two edges, these two one simplices, then there exists a two simplex which fills that in. And it's basically saying that that there's going to be a composition. Okay? So I don't know if that answers. Not necessarily unique, but it's going to sort of be unique up to, I mean, then there's the horn condition for n equals 3 is going to tell you the uniqueness. Yeah, that's the idea.
So can you see this in terms of the algebra or the Ron complex? I mean, there's a relationship between the rational and the Ron complex using solar simplices, right? So can you see it that way?
I'm sure you can. I haven't actually thought about it too much recently. I wrote that preprint quite some time ago. Yeah, I'm sure you can write this down without talking about higher stacks and stuff like that. Yeah, I think so. But I mean, it has to do. It does have to do with the Hodge structure. So it's not just a pure rational homotopy thing. Remember, the Kadar-Spencer map is telling us how the Hodge filtration is varying. So it's going to have to deal in some way with the Hodge structure. And it's kind of, I mean, it's going to be, if in this example you write down the reason why the Hodge structure does not vary when you move in a single tangent direction, then sort of put those together, you have a secondary class which tells you that what's the obstruction to having a uniform reason why, a uniform trivialization of the Hodge filtration over the tangent space. So I'm sure you can write that down by, I don't know how to do it. But, Thank you for listening.